Hi all, welcome back. And in last lecture, we learned about performance of paging. We'll try to continue this performance of paging part in this lecture by solving certain questions on this performance of paging. So, from last video, we know that EMAT, effective memory access time, okay, effective memory access time using TLB is nothing but a translation look aside buffer, is equal to x into 1 c plus m plus 1 minus x into c plus 2m. Okay, where x is the hit ratio. Hit ratio means that the page that the CPU or the processor is searching is found in the TLB section. Okay, so if the page is found in the TLB, then the hit ratio, then it's a hit, and if it is not found in the TLB, then it is a miss. So we already talked about how we calculate this formula. Now let's solve some questions depending on to this formula. So let's say we have a system. Okay, and for this system, the main memory access time. Okay, so main memory access time is given as 100 nanosecond. Okay, now the TLB access time, so TLB is nothing but is hardware implemented with the help of associative register. Okay, so TLB access time would be very less than the main memory access time, so it is 20 nanoseconds. See the difference between these two. Now let's say that the TLB hit ratio. Okay, so you would be given the hit ratio. That is the probability of finding the page in the TLB is 80%, or let's say it's 95%, very high. Okay, so now if we need to calculate the EMAT with TLB and without TLB. Okay, so let's say it is without TLB first. So if we don't have any TLB, then definitely, let's say without TLB, if we are calculating, if we don't have the TLB, then definitely first we need to look into the page table, which is present in the main memory. So 100 nanosecond plus again we have to look into the main memory for the particular page, so that will be also 100 nanosecond. So altogether we are utilizing 200 nanosecond if we are not using the TLB. Okay, so this is without TLB. Now let's say we have this TLB. So with TLB, if we need to calculate the effective memory access time, so it will be x. So from the formula, it will be 0.95, that is the hit ratio, multiplied by TLB access time 20 nanosecond plus main memory access time, because first we are searching the for the frame number of the particular page in the TLB, and then we are accessing that particular page from the main memory. That will take 100 nanosecond plus, if it is a miss, let's say for 0.05 it is a miss, so in that case we again have to access the TLB, sorry, we have to access the TLB, which will be a waste because that page won't be found here. Then we have to again access the uh, page table, that will take 100 nanosecond, and then again we have to access the main memory, that will take 100 nanosecond. So altogether is 200 nanosecond. So the answer will be something like this, and here you get 0.05 multiplied by 220. So you can do the calculation, of course, and here we'll get if we multiply it, get 114, and if we multiply this, it supposed to be 11. So altogether is 5 to 125. So altogether is 125 nanosecond will be taken for for the accessing time, EMAT, with TLB. So see how the effective memory access time has been reduced to 125 nanosecond from 200 nanosecond just by introducing this TLB part. Okay, so this is what I wanted to discuss. Now there will be some other questions coming up, like let's say we have a system. Now we need to calculate the hit ratio. So we have to find the hit ratio so that the effective memory access time reduces from 300 nanosecond without TLB to 250 nanosecond with TLB. Okay, this 250 nanosecond is with TLB and 300 nanosecond is without TLB, right? So now to solve this question, this is without TLB. So 2 times access time is 300 nanosecond. So from here we can calculate the main memory access time is 150 nanosecond, right? Now without with TLB it is 250 nanosecond. Let's say that the hit ratio is x. So x multiplied by c plus m plus 1 minus x multiplied by c plus 2m, that is equal to 250 nanosecond, right? Now we have this m, that is 150, and we have this 2m, that is 300, right? So we can just simplify this as xc plus 150 x plus uh, c plus something like, we can do this calculation like that. So from here we get sorry, it's c plus 300 minus c x minus 300 x equal to 250 nanosecond. Now from here we can do some like reduction, like xc is cancelled, and then from this becomes c minus 150x plus 300 equal to 250, like this. So I believe it will be something c plus, okay, so it's c plus 300 and xc minus 300, so it will be we can take it into here, so it becomes minus 50, or else we can do 150 x minus c equal to 50. So let's say we need to find out the hit ratio. That means we need to find the x, and here are the true variables. So let's see if it is 250 nanosecond. Mm-mm-mm. So we need to have at least one variable here, like we need to have the c, that is the TLB access time. So let's say TLB access time is, I think, given in the question. Let me search for that. I think it is given. Yeah, it is 60 nanosecond. So unless and until it's not given, we can't solve this, right? There are two variables here. So now we have this 60 nanosecond. So 150x minus 60 equal to 50, and x equal to 110 upon 150 is equal to 11 upon 15, and this can be written as 73.33%, something like that. So we have this TLB hit ratio is 73.33%. So this way we can calculate, but here just note that at least one thing has to be given. Either we need to be given hit ratio, or we need to be given that TLB access time, okay? Because these are two variables, we need at least one for solving this. So this is one type of question where you are asked to find out the hit ratio, or you can be asked to find out the effective memory access time. Or let's say we have another question, like we have one system, and this system has a logical address of 32 bits, okay? So 32 bits is the logical address, and we have the page size of LAS, that is equal to 4 kilowatt, okay? From here we can find the number of pages. So the number of pages equal to LAS upon page size. right? So if it the LA is 32 bits, so LAS will be 2 raised to the power 32, right? Word. Okay, so it will be something called 2 raised to the power 32 word by 2 raised to the power 12 word. So it is 2 raised to the power 20. So P is equal to 20, right? So we have got the P term, and D we already know from here we can get is equal to 4K pages would be there. So it will be 2 raised to the power 12. So D will be 12. So this we can get it from this part. Now, memory is word addressable, it is understood. And PTE, page table entry, is equal to one word. Okay. So PTE represents what? It does contains the frame bits and everything. So altogether the PT is one word. So if we are asked about page table size, so page table size would be nothing but PTE multiplied by number of pages. Okay, because for each page we have a page table entry in the page table, so it will be one word into 2 raised to the power 20, that is 1 MW, right? So this is the page table size. Well, this is not about effective memory access time, it is actually calculating about the page table size. So these are the various questions that will come from paging. And just to recapitulate, or sorry, revisit the part of performance of paging, I like to illustrate it once again so that the concept is clearer, how we are uh, reducing the memory access time with the help of TLB, right? So if we don't have the TLB, so case 1 is we don't have TLB not present. Okay, so just we have the page table, and from the page table we just have to look into the mess. So the ideal condition is like the CPU is there, and the processor generates a logical address. So this is the logical address. Now this logical address contains two terms, that is P and D. So P represents the page number and D represents the page offset. Now let's say it has generated this, and now here we need because in the main memory we have stored the pages in different frames. Okay, so let's say we need here the frame number and the page offset. So the frame we need the physical address. Now this page has to be mapped with frame, so definitely we need a translation table. So this is the translation table, also known as the page table. Now in this page table, for every page we have the corresponding frame number associated. Okay, so if there are 2 raised to the power 3, that is 8 pages, right? So for that 8 pages we have corresponding frame number in which the page is present. So let's say that these are the frame numbers. Okay, and in corresponding frame we have the pages present. So let's say page 1 is present here, page 2 is present here, page 3 is present, and page 4 is present, right? Like this. So here this part will contain the page number and this part will contain the frame number. So let's say for 0, 1, 2, 3, 4, 5, 6, 7, for each page number we have the corresponding frame number. So let's say page 0, we don't have any frame number associated with that. For the first page it is present in 00 frame, for second page it is present in third frame, right? So sorry, the second page is present in the first frame. Okay, so corresponding like second page, first page is present in second frame, sorry, first frame. No, the first page is present in 00 location, that is the zeroth frame. Let me take it into binary, that will be easier. So 001, 010, 011, and so on. Okay, so the first page is present in zeroth frame. The second page is present in first frame, that is 01. The third page is present in um, second frame. Okay, so it will be 10, and the fourth page, that is 100, is present in the third frame, that is 11. And for remaining, we don't have any entry, right? So from here, this will take that, if whatever is the page number and corresponding frame number will be taken, and from here we can go inside the main memory and get the page, right? So all both these tables are stored in the main memory. So accessing, first we are accessing this part, that is the page table, which takes m time, and accessing this also takes m time, because both are present in the main memory. So it takes twice the 2m time to access these two. So without TLB, the total memory access time will be 2m. Okay, now this is the normal case. But now we have introduced in the second case TLB. Okay, so the translation look aside buffer is used. So now what happens, that when the CPU generates a logical address consisting of the page number and page offset, so first this is looked upon into the TLB. TLB is nothing but, you can assume as a cache for the page table. So in the page table, where we have entries for all the pages present, here it contains some of the page, and for some of the page we have the page entry, like it contains the frame number, and corresponding to the frame number, corresponding to any page number, it contains the frame number. But it won't contain all the pages, like this will contain all the page numbers present in the logical memory, and its corresponding frame number if it is present inside the physical memory. Okay, but if it is not, then it will contain null. But here we are just referring to some pages. So this part is not inside the main memory. This is implemented with the help of associative register. So it takes, let's say, c time. So if it takes c time, then first time you are accessing this part, so it takes c time, and correspondingly you are obtaining the frame number of this memory, which takes m time. So altogether you are taking c plus m time. Let in the case if the page is found in the TLB, so that hit ratio is x. But what if it is not found here? So in case of 1 minus x, that is if it is a miss, then you need to go inside the main memory. So it will take m time to search for the corresponding frame number, and again it will take m time to search for that particular page inside the main memory. So it takes c plus 2m time in case it is a miss. So altogether we are just combining these two into one and saying that with the help of TLB, the effective memory access time becomes x into c plus m plus 1 minus x into c plus 2m, right? So this is the effective memory access time when we are using the TLB. So in this way, I think the figure is not very much clear, but I think if you go back to the previous video, you can just take a look into that, how we are accessing with the help of TLB. So it is just an illustration of the performance of paging, and now we are good to go with paging part and entire paging section. So we have dealt of very different types of questions and also about the performance of paging. Next we are going to look into detail about the two types of paging, that is multi-level paging, and also about the inverted paging, which is also very important part. So we'll go in detail into that. So now I'm just stopping my video here, and if you do have any questions or any comments, then please do post in the comment section. Thank you very much.